Okay, we are moving on today to a different type of hypothesis testing. We're talking about comparing two population means. And we're again starting with the simplest case of the population standard deviation being known. Um, so, if we're wanting to compare two means, what are we meaning by that? Why aren't you changing? There, there we go. So, for example, I made chili tonight, and it turned out a little spicier than the chili my wife usually makes, even though we're using essentially the same recipe. So if I wanted to study this statistically, and that we measured the Scoville hotness of both of our chilies several times, it'd be comparing the means of those two samples to see if the hypothesis that my chili was hotter than hers um, was statistically valid. So again, as with the other hypothesis tests we've talked about, we state the null and alternative hypotheses. We determine which distribution to use, what the test statistic needs to be, and what the level of significance is. We gather the data and calculate any necessary sample statistics, and then we can draw a conclusion and interpret the decision. Same, there we go, laser pointer. Exact same steps we've been doing all along for hypothesis testing. So in this case, there are two different ways to normally write a null and alternative hypothesis when we're comparing two population means. We can state that one population is greater than, less than, or equal to the other. So, for example, my chili is hotter than my wife's chili. That would be the alternative hypothesis. Or, alternatively, my wife's chili is less hot than my chili. Again, equally valid way of stating it. You could write it as this, my chili's hotness is greater than my wife's chili's hotness. And the corresponding null hypothesis that's the logical opposite is that my chili is less than or equal to my wife's chili in terms of spiciness. The second way to phrase these is basically taking these and putting both means on one side of the inequality as like so. So we've moved the mu2 over to this side of the inequality, so that we're phrasing that the difference between between the two means is less than, equal to, or greater than 0. This is the preferred method because it directly relates to this test statistic that gets used. So let's look at some examples. So we want known alternative hypothesis to test that the mean of population 1 is less than the mean of population 2. So as in to say that, my wife's chili is on average less spicy than my chili, for a more concrete example. We can write, here we go, we can write it symbolically as so, mean 1 is less than mean 2. We want to compare them to 0. As in the second method, we can rearrange them so they're on the same side. Subtract mean 2 from both sides and get mean 1 minus mean 2 is less than 0. The mathematical opposite is that mean 1 minus mean 2 is greater than or equal to 0. Let's see, I'm saying mean 1 is less than mean 2. Right, yes, that if mean 1 was less than mean 2, that'd be a negative number, so it should be less than 0. Yeah. Sorry, I just had to mentally double check the math because it's easy to get lost on some of that. So then the opposite is the logical opposite is that mean 1 minus mean 2 is greater than or equal to 0. So we could phrase those in brief like so. That would be a left-tailed test. The right-tailed test, the claim that the mean of population 1 is greater than population 2, or in the chili example, that my chili is spicier than my wife's chili. Um, we can write it mean 1 greater than mean 2. We can put them on the same side. Mean 1 minus mean 2 is greater than 0. Um, as such, mean 1 minus mean 2 greater than 0. Logical opposite, mean 1 minus mean 2 is less than or equal to 0. If we wanted to test the claim that my chili and my wife's chili were equally spicy, we could phrase it as, or not equal, sorry, I guess we'd be testing that they're not equally spicy. Mean 1's not equal to mean 2, or mean 1 minus mean 2 is not equal to 0, because if mean 1 equals, if they're equally spicy, mean 1 minus mean 2 would equal 0, so that gives us our logical null hypothesis here. Right, that should all be fairly familiar at this point. The only real complication is we've got two means in here. We could set up a hypothesis test that the mean of population 1 is more than, is a certain distance apart from the mean of population 2. So we could phrase it like so. The mean of population 1 is greater than the mean of population 2 plus 20. We can again arrange those so it's on both sides. All the means are on one side. The mean of population 1 minus the mean of population 2 is greater than 20. In some ways, this phrasing makes more sense when it's a number other than 0. It's more than 20 units above. It almost comes right out. This is more than 20 units above means the difference is greater than 20. So that this comes more directly from the phrasing than it does when you're comparing them without it. Mathematical opposite, again, is that the difference is less than or equal to 20, which gives us these hypotheses. Okay, so our test statistic, again, we've got some of the same conditions that have to be met that we've had frequently. The samples have to be independent, simple random samples. Sample size has to be at least 30, or the population distributions have to be approximately normal. If that is the case, then we're using a z-statistic, and we're using this equation. We've got sample mean of 1 minus the sample mean in 2. Take that difference and subtract the difference between the presumed population means, or the presumed value of that difference from the null hypothesis. So this would be, it could be 0, it could be 20, it's whatever we have. When we write the null hypothesis in this form, it's whatever we have on the right-hand side of that equation. Mu1 minus mu2 is less than or equal to 0, less than or equal to 20, whatever that number is. That's our presumed difference here. And then these would come from our testing. And then because we're using the population standard deviation known scenario, we'd have the population standard deviations. Actually, I guess this would be variance because it's standard deviation squared over the sample size for each sample set. So it's a slightly more complex calculation for z, but it's still, in essence, the sample related portion minus the population related portion over the square root of something related to the standard deviation. So it's a similar equation, just dealing with slightly different values there. Okay, we went over that. There we go. All right, so let's look at a more specific example. We've got a researcher wanting to test the claim that grocery shoppers spend more when shopping on an empty stomach than when shopping on a full stomach. I believe that's true. I tend to buy more when I'm hungry, or at least it always feels like it. So they surveyed 93 random shoppers, randomly selected. So we've got the randomly selected portion there. Um, leaving a grocery store. Of those surveyed, 41 did not eat breakfast that morning. That group spent a mean of $72.27 on groceries. The other 52 shoppers did eat breakfast that morning and spent a mean of $69.43 on groceries. Okay, let's assume that we know the population standard deviations. Empty stomach is 805, full stomach is 9.22, and we want to use the 0.05 level of significance. So that's our standard deviations, level of significance. We've got our sample sizes here, and we've got our sample means here. All right, null and alternative hypotheses. First step. Let's assign population 1 as empty stomach, population 2 is full stomach. We want to know if they spend more with an empty stomach than on a full stomach. So we're looking to see that the mean in 1 is greater than the mean in 2, right? Mean 1 greater than mean 2, or the difference between them is greater than 0. So that gives us the following hypotheses. The difference between the two means is greater than 0, or the difference between the two means is less than or equal to 0 is our null hypothesis. All right. Which distribution to use? What's the test statistic and what's the level of significance? We're looking at the difference between two populations. We know the population standard deviations. They were independent random samples, and the sample sizes were greater than 30. So we can use... excuse me. We can use the Z statistic and standard normal distribution. That's appropriate. We can use the p-value calculated for that, and the level of significance was 0.05. So if we get all our data together, it looks like so. There's the means and standard deviations and sample sizes for each. I know I pointed those out during the problem, so you should be able to have seen where those came from. Plug those into our formula for the test statistic. There's our formula. Mean of sample 1 minus the mean of sample 2. Take that difference and subtract the value from the null hypothesis. In this case, it's 0 there. So difference between the two means minus 0 divided by this mess. Okay, so there's mean 1, mean 2, so 0, standard deviation for 1, standard deviation for 2, sample size for 1, sample size for 2. We get approximately 1.58. Note we're from the null hypothesis, mu1 minus mu2 is 0. That's from the statement to the null hypothesis. So we're looking at a right-tailed test. P-value for 1.58. Right, so it's the area under the curve, under the standard normal curve to the right of 1.58, which from the tables gives us 0.0571. That p-value is greater than our level of significance of 0.05, which means we don't have enough evidence to reject the null hypothesis. So there's insufficient evidence to show that hungry shoppers spend more money. We could do this on a calculator. It's the two-sample z-test that we're after here. We know the sample statistics, so we start with stats instead of data. And give it the stats that we know. It's a couple screens worth of stuff. You can see where we scroll down just one into, so it's one line below the first screen. Tell it which type of test we want, tell it to calculate, and it will spit out our p-value. If we scroll down a bit, it'll give us the sample size, but there's our p-value. You note that it's a little bit different. Again, that's rounding error. Okay, all right. So we've got two universities in the same state that are bitter rivals. So each university thinks their students are more physically fit than the students at the other university. So if I were to use Washington State, where I'm from, as an example, University of Washington and Washington State University are bitter rivals. I would argue that Wazoo's students probably are more physically fit because it's a much hillier campus. So you walk around on hills a lot more, so that's probably a good claim. So if we wanted to test that claim, they've selected 36 random students at the first university. They were surveyed and exercised for a mean of 2.9 hours per week. Got 38 students at the second university. They also surveyed and they exercised for a mean of 2.7 hours per week. So the assumption here that they're not telling you is that the amount of time spent exercising directly correlates to physical fitness. Okay, so if the standard deviation is known for the two, we've got 1.1 hours per week at the first university and 1.0 hours per week at the second. We want a 0.05 level of significance. And we're just after if there is an average difference in fitness level at the two universities. So as you can see from the title, we're after a two-tailed version here. This is the just looking to see that there's a difference. So we're wanting to show that the average at one is not equal to the average at the other. I'm not saying one's more fit than the other. We're just saying there's a difference. The logical we can rearrange it so it's on one side. The difference is not equal to 0. The logical opposite is, of course, that the difference is equal to 0, so that's the same fitness level at both universities. Okay. So which distribution do we want to use? What is the level of significance? The level of significance was given at 0.05. We'll get to that in the next slide. We're looking at the difference between two population means, and we know the population standard deviations. So we want, and both sample sizes are at least 30, and it was a random sample. So we want to use the z statistic, which has a standard normal distribution. We've got a 0.05 significance level. So we can gather our information. We've got University 1, it was 2.9 hours per week. Exercising at University 2, it was 2.7 hours per week. Standard deviations, 1.1 hours. In 1 hour, 36 students surveyed, 38 students surveyed. Okay, so we can plug those into our formula, as so. So this again is going to be 0 because we're looking at a difference being not equal to 0. So that's going to be 0 there. This is our number of hours exercised at each university, the standard deviations, and the sample size. Right, so we've got 2.9 minus 2.7 minus that 0 from the null hypothesis, standard deviations, and sample size, and that is about 0.82. Um, again, this comes straight from the null hypothesis. Okay, so we need to draw a conclusion. We're after a two-tailed test this time. So the p-value is probability of obtaining a test statistic that is less than or equal to negative 0.82 or greater than or equal to 0.82, which is, the absolute value of z is greater than or equal to 0.82. So the p-value we're after is the sum of the areas under the curve to the left of negative 0.82 and to the right of 0.82, like so. Out here plus out here. So we've got that p-value plus that p-value. If we use the either technology or table, we get a 0.4122. Might be slightly different with the calculator due to rounding again. That is much greater than 0.05, which means we don't have enough evidence to reject the null hypothesis. There's insufficient evidence to show a fitness level difference between the two universities. Again, we can do that in the calculator. Two sample z-test with statistics as the input. This time we're selecting the not equal to. If we calculate it, it spits out our p statistic right there. It also gives us the z value there. Again, that's slightly different because it's not using. It's got more digits. It's still probably rounding at some point, but not in not anywhere where we can see. Okay, last example. We've got a drug manufacturer claiming that its new cholesterol drug with a healthy diet and exercise plan lowers patients' total cholesterol by over 20 points more than simply changing the diet and exercise regimen. So we've got 55 patients with high cholesterol chosen to take the drug in addition to changing their diet and exercise plan. Over 3 months, this group lowers its cholesterol by a mean of 44.7 points. Somehow we know the standard deviation for this group to be 6.8 points. We've got a second group, 55 patients with high cholesterol. They change their diet and exercise regimen and don't take the drug. Maybe they're on sugar pills instead, as a typical blind trial would have. So they still think they're taking something similar. They lower their total cholesterol by a mean of 23.1 points. Population standard deviation somehow known to be 5.3 points. We want to test the drug manufacturer's claim using a 0.01 level of significance, so 99% level of confidence, because we want to know this for sure, or as sure as we can, just about. So first off, let's think about the null and alternative hypothesis. Let's give populations numbers. We'll set number 1, group 1 is the patients with the drug, group 2 is the patients without the drug. The manufacturer's claim is that it's a more than 20-point difference. The means being tested represent the amounts by which the patient's total cholesterols are lowered. So this is the mean number of cholesterol points lost. So we're claiming that group 1, the mean number of points lost is greater than the mean number of points lost in group 2 plus 20. So this is the alternative hypothesis. We get these both on one side. Mean 1 minus mean 2 is greater than 20. Right, and then we've got the logical opposite, that mean 1 minus mean 2 is less than or equal to 20. So the difference between the groups is smaller than 20, essentially. So our research hypothesis that it's greater than 20, null hypothesis that it's less than or equal to 20. So which distribution to use, what test statistic, what level of significance. Again, we're given the level of significance is 0.01, so that's not a hard question in this case. We're looking at the difference between two population means. We know the population standard deviations. We know that they're independent random samples, and the sample sizes were both 55. So we're going to use the z statistic, which is standard normal distribution. Again, we've got a 0.01 level of significance. That's given. So we gather our data. We've got a mean 1, 44.7, mean 2, 23.1. It's looking good so far, right? The question is the difference between these two important? Standard deviation 6.8 and 5.3. Sample size is both 55. Plug this into our formula here. Mean 1 minus mean 2. Subtract the presumed difference between the means, which we can get from our null hypothesis, as 20. In this case, we want to show that it's greater than 20 or less than 20. But 20 is what we'll use there. Then we've got the standard deviations and the sample sizes as such. There's our means, standard deviations. It is going to be important to double check that you're putting the right group's mean in order here, otherwise you'll have a sign error in that and get a different answer. So if we do this, we come up with approximately 1.38. And again, that's 20 there, comes from the null hypothesis. So, draw our conclusion. We're looking at a right-tailed test because we're trying to show that something is greater than, so that points us to right-tailed. So we're after a p-value of greater than 1.38, or the p-value associated with 1.38, so it's the area to the right of 1.38 and the standard normal curve as such. And that area is 0.0838, which is greater than 0.01, so we don't have enough evidence to reject the null hypothesis. We don't have enough evidence to support the manufacturer's claim that their drug combined with diet and exercise will lower a person's cholesterol by more than 20 points compared to changing diet and exercise alone. One thing to note here is we cannot do this one on the TA8384 because the hypothesized difference is not 0, and the calculator does require that. I have not looked into whether you can use a non-zero hypothesized difference in Excel. I want to say I would expect you can, but might not. Alright. That is it for this topic. We will move on to talking about what to do when the population standard deviation is not known next.